Another semiconductor device that we need to be familiar with is called the field effect transistor. And there are different types of field effect transistors. And what I want to explain here is the principle behind the operation of the field effect transistor. Again, the knowledge of the semiconductor principles here are not critical because we're going to develop abstraction models. But I do want you to be familiar with how we can use the doped semiconductor materials to create these things called field effect transistors. So a field effect transistor, if we look at a cross-sectional view, how it's made is that there's some type of bulk material, and in this case we're going to look at what's called an N-channel field effect transistor, or an N-channel FET. And inside of this P-type material, because it's an N-channel field effect transistor, we have these wells that consist of or are comprised of an N-type semiconductor material. And then between those two wells, we have this layer of metal oxide. Now, you may recall or may have heard from either chemistry or materials that metal oxides are not good conductors of electricity. So in this region right here, we're going to have something that does not conduct well, and then we're going to have a metal contact to that. And these two wells in this metal contact have special names associated with them when we're talking about a field effect transistor. And we call the one that's connected to the contact, that's connected to the metal oxide here, we call that the gate. And then the two other ones that are connected to the N-type well, in this case, are the source and the drain. Okay, so if we take our field effect transistor and we look at sort of the band structure through the material from the N-type to the P-type to the N-type, we can draw a energy diagram that looks something like this. And you see that between the P-type, there's this barrier to electron charge carrier transport. So the electrons will have to have significant energy to go from one N-type well to the other N-type well. Okay, so that's sort of the basics behind this. Now there's a this is the case where we have no applied potential anywhere in the system. So now we're going to look at what happens if we first connect the drain and the source together with a voltage supply. So we supply a potential difference between the drain and the source, and we call this VDS because it's the potential difference between the drain and the source. Alright, so when we apply this potential difference, we know that when we apply a positive potential difference, our Fermi energy level is going to shift downward in this direction. And we see that actually by doing this, what happens is we're going to increase the potential energy barrier to charge transport in this direction. So electrons will certainly not be able to overcome the barrier here, and we do very little to change the barrier in this direction. But what does happen, since we're adding more positive charges on this drain well right here, we're going to attract some more negative charges, free electrons, that are able to move around throughout the crystal, and that will be occupying the valence band, or excuse me, the conduction band in this region right here. Okay, so that really doesn't help us though, because we're still not getting any current through this system because we don't have any net motion of charged particles. So now what we're going to do is we're going to also take another power supply, and I'm going to draw that in here, and connect it between the gate and the source. Okay, and this source, this we call VGS because it's the potential difference between the gate and the source. And when we do that, we're also going to shift the energy level down between the gate here. So what's going to happen is we're going to apply some positive charges over here on this contact to the metal oxide, and because the metal oxide does not conduct anything, we're not going to have any net motion of charges there, but we are going to establish this attraction force. So some of the charges that are available that were the excess negative charges here are going to sort of migrate towards this interface as we apply a potential across the gate. So we're going to get a redistribution of these negative charges, these free electrons, and what that basically is on our band diagram is a lowering of the energy level here and a lowering of this potential barrier to electron transport. So when we do that, our charge carrier region now becomes enhanced, and we actually create a path through which electrons and positive charges, the holes, can move. So in this case, if we apply sufficient potential to the gate, electrons from the source will be able to move freely through the material because they're going to go down in energy, and our holes are going to have motion because they're going to want to increase their energy. Alright, so that's sort of the basics behind how the field effect transistor works and why it's a little bit different from the bipolar junction transistor. In particular, this gate right here, which is analogous to the base of a bipolar junction transistor, there's no current, there's no net flow of charges that moves from the gate contact into the semiconductor material. So that's the primary difference between a field effect transistor and a bipolar junction transistor. Now, all of that is fantastic and great, and I want you to have an idea of how these different devices are formed using semiconductor junctions, but we are going to develop an abstraction model to help us explain how this behavior occurs. So a field effect transistor, just as we said, is a semiconductor device that is comprised of multiple arrangements of P and N type material. So the one that we talked about was called the N channel FET. We also have a P channel FET, which has the wells comprised of P type material and the body comprised of N type material. A FET has three terminals that are important, which are the drain, the gate, and the source. And there are different types of FETs that we can have. There are junction field effect transistors, metal oxide semiconductor field effect transistors, there's enhanced mode, depletion mode. We're not going to worry about all of the different types. That should be left for an advanced course in semiconductor devices. But what I want to get across here is that the field effect transistors are used to amplify or switch signals, and they're usually used for faster switching or larger power applications than bipolar junction transistors. So if we take a look at our abstraction model, first of all, up here we see two different symbols for the N-channel field effect transistor and the P-channel field effect transistor. There are a bunch of different symbols depending upon what type of field effect transistor it is, but these are kind of common here. You may also see these enclosed in a circle, so that would also represent a field effect transistor. But as you saw, basically what we're doing is we're controlling the amount of current, the amount of charge that can pass between the drain and the source by controlling the potential difference that is developed across the gate of the device. So the field effect transistor acts as a voltage controlled current source. So unlike the bipolar junction transistor, which was a current controlled current source, the field effect transistor acts as a voltage controlled current source. So the important implication of that is that we do not need to supply additional current. All we need to do is somehow develop a potential across the gate to control the current. Now, of course, as with the bipolar junction transistor model, this model is valid only in a particular region of operation, and that particular region of operation is called the linear region of operation. The linear region of operation occurs, and this is also called the ohmic mode, because the field effect transistor is going to act like a variable resistor, where the resistance depends upon the potential between the gate and the source. Now, the linear region of operation occurs when the drain to source potential is less than the gate to source potential, or the gate to source voltage. And in this mode, we can use the field effect transistor to behave as a variable resistor, where the variable resistance depends upon the voltage applied to the gate and source. The other common way to operate a field effect transistor is in the saturation region, and this occurs when the drain to source voltage is higher than the gate to source voltage. And in this region, we're conducting, this model no longer applies, and essentially the drain to source is no longer a current source. It's just going to act as a wire that allows some maximum amount of current to pass through between the drain and the source. And that current that it allows to pass through depends upon the applied gate to source potential. So in the linear region, we can apply this model right here. And in the saturation region, this effectively acts as a switch that's going to control the drain to source, how much current passes between the drain and the source. Okay, so we have two regions of operation. We can make it act as a variable resistor in the linear region, or as sort of a switch in the saturation region. And that's primarily how we're going to view the field effect transistor, as a voltage controlled switch through the projects and the analysis that we're going to do in this class.